for this presentation. Here we will talk about high mobility channel materials and novel devices for scaling of nanoelectronics beyond the silicon roadmap. So obviously I think we all know that the electronics industry has been driven by Moore's law over the years, which means we made an enormous progress to scaling, always trying to make smaller and faster transistors. And this just shows you in 40 years of scaling what it has been doing, going from transistors which were actually 10 micron gate length down to transistors nowadays 32 nanometers. It also shows the enormous gains that we have made in terms of speed, number of transistors that we have on a circuit, and actually all of that has gone together with a relatively small increase in the size, but definitely a fantastic increase in performance. So this has been driven always by the fact that we always go for transistors with higher and higher drive currents, because the drive current determines the speed of our final circuits. And this drive current depends one over the length of the transistors, so that's why we have been doing scaling. It depends on the oxide thickness, so that's why we have been going to high K metal gates over the last years. And obviously it also depends on the mobility of our carriers, so that's why we have built in strain in our devices in order to improve our mobility. So the question that we will address now in this presentation is, can we use this mobility factor here to even further boost the performance by using high mobility channel materials? So go away from silicon and use materials with a higher mobility. First of all, the important question we have to address is, and I will not go into very much detail about it, but the important question is, does mobility really matter for these very small devices? Because I think over the years many people have been talking about ballistic transport that you have in very short channel devices, and if you have real ballistic transport limit, normally mobility loses its meaning. However, I think people have figured out that having materials with a low effective mass is still very important, because it actually determines the source injection velocity, and the source injection velocity still is related to 1 over the effective mass, so in that sense is still related to the mobility of the materials. And that still determines to a very large extent how much drive current and how much speed we will have in our transistors. So if you look to the table of materials that we have available, we see that we have actually a whole list of materials that do have high mobilities. But for example, very interesting material that comes out here is the germanium, very high interesting hole mobility. Obviously, we have the 3-5 materials here that all have very interesting electron mobilities. So the question is, if this is so obvious, why have this not been used in the past? Well, I think the big difference between these materials and silicon is very simple. I think with silicon we have this fantastic, beautiful interface between the silicon and the silicon dioxide, which actually gave us the possibility to make MOS kind of devices. Unfortunately, we don't have that for these high mobility kind of materials. So electrical passivation of these materials is a major question, and it's a very big challenge. Secondly, it's not all about mobility, but as I said in the beginning, it's about drive currents. And currents is actually the multiplication of mobility times the number of carriers. So for example, if you look at some of these 3-5 materials, you see that many of them have actually very low effective masses, so very high mobilities, but they have also very few carriers actually in the values that have these low effective masses. So for example, this is a typical value that you see for gallium arsenide. You see that here you have the very sharp edge, so that the second derivative gives you a very low effective mass, but you also have pretty low density, and pretty soon your carriers actually will fill up in these other values here that have higher effective masses, so actually you cannot carry that much current. So in order to have a good material, you need actually a combination of high mobility and high density of states. So that's why it's not so obvious always just to go to a high mobility material. But okay, I think people in the meantime have been demonstrating that by the combination of high mobility materials and the scaling, I think we can make devices that are definitely outperforming silicon, or have the potential to outperform silicon. That's what I will focus on in the rest of this presentation. So what we try to make actually is we use the silicon substrate as a carrier. We can still actually make, if you want, standard CMOS on the silicon substrate, but we focus actually on the high performance CMOS core, where we propose that we have either germanium or other 3,5 materials probably at the end, but we will start with germanium to make the PMOS devices. We use indium gallium arsenide, which has this good combination of high mobility and density of states to make the NMOS devices. So in order to make this technology, we need to develop a few key technologies. One of it is, first of all, is the selective growth of these materials onto the silicon. Secondly is the high K-gate stack. Third comes the kind of devices you want to make with it. And then fourth of it, how can you further boost the performance and mobility in these devices. So let me first talk about one of the major problems, especially if you want to go with these things into real production, is how can we get the germanium and 3,5 materials onto silicon. For that we have been using a very simple approach, so to speak. What we do is we start with a standard silicon wafer. We go through the standard shallow trench isolation process, as we call it. So we have these silicon islands that actually isolate these various silicon parts here. What we do then is in an HCl environment into our epi reactor, we etch out the silicon and we regrow germanium in these trenches. So only locally where we need the germanium, we will grow the germanium. This, for example, is a cross-section SEM picture of germanium that we grow in that way. We can use the same trick for 3,5 materials. This actually shows you how it works, for example, for indium gallium arsenide, where in the same trick, locally we can implement this indium gallium arsenide only at the places where we need it. The reason why this works so well is because we use what we call the aspect ratio trapping. If you have a shallow trench and you have the right ratio of depth versus width of the trench, actually all the defects that you will generate here due to the lattice mismatch of these two materials will give you defects that grow out in a certain direction and actually will end here at the edges of our STI trench. Meaning that if our aspect ratio is large enough, at the top here of the trench we will have pure material without defects. And we can have two kinds of implementations for this. We can do this in some kind of planar implementation where we add CMP to the whole technology, or we can actually outgrow this material and directly make FinFETs that give us the advantage of having even further improved electrostatic control. For germanium, this definitely works very well. For 3,5 materials, there are actually some added issues on top of it. The basic problem that you have with 3,5 materials on top of the germanium is that it's a polar semiconductor. So that means that you try to grow a polar semiconductor on top of a non-polar group 4 semiconductor surface. If you look to that in more detail, you see that every time you have a monoatomic step and you grow gallium arsenide, for example, in it or any other 3,5 material, you will end up with places where you will have arsenic and gallium bonds, which we call anti-phase boundaries. And these are electrically active defects. How can you avoid this? Well, you can avoid this by having surfaces which only contain double steps, because then by the time your two layers that you grow on the various terraces, by the time they meet, actually they are nicely aligned again, and you do not have these anti-phase boundaries. So normally this is done by using miscut substrates, but we obviously want to avoid using miscut substrates because 300 millimeter or 450 millimeter miscut substrates are not that easy to handle. So actually we figured out another solution for that, which again looks relatively simple and relatively straightforward. We again start with the same STI approach. So we take our silicon wafer, etch out the silicon, but in this case we etch it out a little bit further. So we actually make a slight hole into the silicon. We deposit germanium on that and we let the germanium flow. And if we have the right etching depth here and the right etching width, actually we make a very big curvature here, and that curvature will translate into double atomic steps, because these double atomic steps gives the lowest surface energy of the system. And that is actually the ideal surface that we need then again to grow the 3,5 materials without having anti-phase boundaries. So this, for example, is a very nice example of where we have grown such a structure. You see the silicon, you see the germanium that we have put it here on the bottom, then the gallium arsenide, indium phosphide, and you see the very nice, on this case, a FinFET-like structure here on top. So this means that I think we have a very good outlook on growing these materials onto silicon substrate. That I think is already the first problem that is solved. Second problem is passivation. Why is passivation such a problem? Well, first of all, it starts with the germanium system. I think we know that the germanium oxide system looks pretty similar to the silicon dioxide system. If you look at this picture and you look to the kind of ab-initio modeling that people have been doing for silicon dioxide, it looks basically the same. You have one monolayer, a little bit more, where you have some suboxides, and directly you form actually very good germanium oxide. And if you look to this structure, it actually passivates the germanium very well, and it gives you very low germanium dangling bond densities, which are, without hydrogen passivation, actually even lower than what you find for silicon. So this is actually even a better interface intrinsically than the silicon dioxide interface. So why doesn't it work? Why went people from germanium to silicon so many years ago when they made it MOS devices? Well, actually the reason for that is very simple. First of all, silicon dioxide is very stable. Germanium oxide is not very stable. It has a much higher vapor pressure, so it actually starts to vaporize at much lower temperatures. Also because the germanium oxide bonds are much weaker than the silicon bonds, it also gives a weaker structure. And last but not least, I would say, also the hydrogen passivation does not work on the germanium dangling bond. So the trick by just using at the end a hydrogen anneal forming gas anneal to passivate all the defects does not work on germanium. So this shows you what happens when germanium oxide reacts with moisture. You just actually form GeO. You completely degrade your oxide quality here, and you make actually a lot of defects that obviously kill your device performance. And you can see this especially very strongly if you scale your ELT level to actually very low levels. Many people have reported actually good mobilities, both for NMOS and PMOS devices with large ELT levels where you can keep these defects sufficiently far away from the interface here. But if you scale down your ELT, you really run into trouble with all the defects that you have here. So what can we do about it? Well, the first trick is again a very simple trick. We make the germanium surface look like a silicon surface. We take germanium, we deposit a few monolayers of silicon on top of it, then we translate these few monolayers of silicon into a silicon dioxide layer and put high K on top of it. This looks very straightforward and actually allows us to reuse everything that we know from silicon high K work that we have been doing over the years to translate it to germanium. Obviously, there's a little bit more to it. It depends very strongly on how you grow these few monolayers. And by the way, first let me point out again that it's actually, I really like this TM picture because it shows, I think, the extreme control that we have about these monolayers here. And I think it's a very well-defined process. But we had to work actually quite hard on it. We actually had to make sure that we could do epi at low temperatures to avoid any intermixing here of the germanium and the silicon layer. And we really had to count and optimize the number of monolayers to have the best DIT profile. So this is DIT profile as a function of the band gap of the germanium for two epi deposition temperatures, various amounts of monolayers. And you really see you have to go to a very precise optimization here to get an optimum result. But if you do that, you can make very good devices with it, no problem. These are germanium PMOS devices. We have scaled ELT down to 0.85 nanometers, so you can get very low ELT levels. And these actually are very good, very high performance devices. If you look to them in a little more detail, you see that actually they outperform silicon. But then again, you have to take into account that the real competition is not silicon. The real competition is strained silicon, because we also boost mobility in silicon by using strain. So that means that if you look to the relative ballistic hole velocity as a function of the compressional stress for strained silicon and for germanium, see that also for germanium we will have to build in a certain amount of strain in order to be able to beat strained silicon. So that means we need something at least something like 1 gigapascal of strain into the germanium to be better than strained silicon. And that is something that we can do by using the same trick as people use in the PMOS devices in silicon, where they use the silicon germanium source drain. We can actually replace the silicon germanium by germanium tin in this case. You just look further in the table 4 elements. And that way we can make compressively strained germanium devices that outperform strained silicon. So that's all good news. The only problem is that this kind of silicon passivation only works on PMOS devices. It doesn't work on NMOS devices, because on NMOS devices actually the carriers will be in the silicon instead of in the germanium. So that's why we also have been exploring some other ways of passivating the germanium by doing things like in situ passivation, combining things like sulfur passivation with in situ deposition of high K materials. For example, this is a result of H2S molecular beam passivation combined with aluminum oxide deposited in our MBD tool, so our 200mm MBE cluster tool, showing that if you do this in the right way, you can actually get very nice CV curves, very low ELT levels, but probably doing things in an MBE tool in a production environment is not really that practical. So we can do similar things actually in our ALD tool, and there actually we do find some pretty interesting results. We see that actually the DIT level, again as a function of the band gap here, depends very strongly on the precursor that we use. So this is aluminum oxide, either deposited with water or ozone as a precursor, and we actually see that the DIT profile is clearly different. The reason for that is that in one case, with water as a precursor, we end up with a gate stack which is free of germanium oxide, and actually we come with a DIT profile which is good for PMOS devices. With ozone as a precursor, we actually make germanium oxide sulfur kind of layers that actually gives a low DIT in the mid of the band gap and close to the conduction band gap, and actually is good for NMOS devices. This actually was figured out by XPS measurements that I unfortunately don't have the time to discuss in more detail here. We understand the reason for that, and the reason for that actually comes from the different reactivity of the germanium OH bonds and the germanium sulfur bonds to water and to ozone. But I just, again, without going into much detail, want to point out here that if you look to these energy reaction coordinate curves here, that you see that there's a big barrier to remove the sulfur hydrogen type of bonds, meaning that these are actually very stable on the surface, while the TMH actually can remove them. The TMH can also remove the germanium OH bonds. So the TMH works on the sulfur passivated and the OH passivated surfaces, while the sulfur bond on itself is stable, and that's why you make this germanium oxide kind of layer on the surface. So okay, I think for the germanium we have various solutions. The question is, can we do something similar now for the 3,5 materials? First of all, I want to point out here that I think over the years we've been spending quite a lot of time in learning how to analyze these surfaces, because many people actually came from the world of the silicon business, and actually they were using the typical ways of measuring interface latencies and defects on silicon, and just transferred that to the 3,5 materials, forgetting that you work here with materials that have a different band gap, different time constants for charging and discharging of the traps, and different minority carrier generation times. So what you really have to do if you want to completely scan the band gap in 3,5 materials is you work with P-type and N-type materials, you work in a broad range of frequencies, and you have to work actually at various temperatures to see various parts of the curves. So this actually shows here all the typical illustration of the kind of measurements that we do. This is the DIT profile as a function of the band gap for indium gallium arsenide. And you see that on the P-type at low temperatures, we scan this part. The P-type at room temperature, we are scanning a different part of the band gap. With N-type at room temperature, we are scanning this part, and at low temperature, we are actually scanning this part. And the profiles that we see always actually have a very typical profile. We always tend to see 4 peaks, 2 peaks at the outer edges, and 2 peaks at the center. This actually is an example for gallium arsenide, where actually you very clearly see always these very 4 peaks. And I think we even more or less are figuring out where these peaks are coming from. And I think especially the center peaks here, these are the ones that cause the Fermi level pinning. I think are very difficult ones to remove because they come from structural defects in the gallium arsenide layer itself. The reason why you make them is actually they come from the stress that you generate in the material by growing the oxide that makes gallium and arsenic diffuse into the oxide, leaves arsenic vacancies or leave gallium vacancies, make arsenic kind of bonds that actually are electric kind very active defects, which are present then in the bulk of the material. So not at the interface, they are really in the bottom in the bulk of the interface, very close to the interface, and that's why they give this very typical shape here and this very typical Fermi level pinning. The ones which are more at the edges, we think they are more related to arsenic dangling bonds and gallium dangling bonds. And these are the ones you can easily get rid of by doing sulfur passivation, things like that, or other tricks to passivate the surface very well. But these two central ones here actually are the difficult ones because they mean that you are not allowed to oxidize the surface because even if you remove the oxide later on, you still will have formed these bulk defects. So that is a big problem for 3.5 materials. It's not only about interface states, but it's also about states actually in the bulk of the material. This is also why things like surface reconstruction, for example, are very important on these materials. Again, this illustrates this point for gallium arsenide. We start with an arsenic-rich surface reconstructed at 300 degrees C. You can go all the way to a gallium-rich surface 4 times 6 reconstructed at 580 degrees C. And then if you do in situ MBE deposition of aluminum oxide on these surfaces and you measure the DIT profile, so the DIT density as a function of the energy of the band gap, you see that for the arsenic-rich profile, so the one grown on this surface, you actually have this very big peak here at the center of your band gap. For the gallium-rich surface, you actually see a low DIT level. So this actually points to the importance of controlling your surface condition very precisely and making sure that you start with the right surface reconstruction, the right chemical condition of the surface before you deposit your high K on top of it. Other examples of high K layers that give us very good results are, for example, this is indium gallium arsenide case, the typical gallium gadolinium oxides. Again, by doing everything in a UHV environment under very well controlled conditions, we can get very low DIT levels with it. So again, this shows the comparison with aluminum oxide deposited with ALD, or the UHV gallium gadolinium oxide. The dark blue here, you see that at the gallium gadolinium oxide, you definitely get lower DIT levels, especially here again in the middle of the band gap. Is what we get with aluminum oxide ALD, which again points to the importance of this UV treatment, controlling the surface and making sure that whatever high K you deposit on top of it doesn't disturb the surface conditioning. Other results that we have obtained which are very promising, for example, is a combination of in situ aluminum oxide to passivate the surface combined with hafnium oxide that obviously gives a higher K value. This allows us to scale the ELP a little bit further. We have been able to scale below 1 nanometer ELP with this, and also actually gives us very good DIT profiles. So again, I think there is a very positive answer here. I think we have learned various ways of controlling the interface state density, and I think we know very well how to passivate the 3.5 surface. Does it answer all of our questions? Well, not completely, because there is another big difference between silicon and 3.5. And this again points to what I said at the beginning of the presentation. 3.5 materials have lower density of states, which means that if you want to make an inversion layer in a 3.5 material, you do not have to move your Fermi level just up to the conduction band. Actually, you have to move it far into the conduction band just to generate enough carriers. This again is something completely different than in silicon. In silicon, we have the high density of states. If you move your Fermi level to the conduction band, you have sufficient carriers and you have a complete inversion layer. Here, the Fermi level really moves inside the conduction band, which means that also the defects and everything happening actually at the bottom of the conduction band also becomes important. So that's another complication. Moreover, due to the fact that we have materials here with a low effective mass, it means that these carriers will also tunnel into the oxide much easier, and you will have much more interaction with what we call border traps. So these are traps located in the oxide, very close to the interface, that can easily exchange charge with the silicon due to the low effective mass of the carriers, giving them actually a very effective short tunneling time or actually a long tunneling distance. So we went to quite some detail in simulating all these curves, simulating border traps, simulating this effect of the Fermi level that actually moves into the conduction band, measuring these border traps as a function of position into the oxide and energy. And actually what we see is that also now in the performance of our devices, actually these border traps, which are located above the conduction band, into the oxide, which is shown here in this graph, and typically gives you this kind of distribution, this shape here that you typically see in the CV curves, which many people tend to discard, but actually is very important because this is actually a nice signature here of these border traps that also exchange charge with the 3,5 material, in that way affect our device performance. So this is energy here, this is position into the oxide, and here you see the red part here, it gives you a high density of traps in the oxide. Again, I think this the only way to solve that is by depositing the right high K material and annealing it in the right way. So again, all the learning we had from the high K work on silicon, I think, comes very handy here in order to optimize our high K stack. So that's why I put, I think, both the growth of the materials on silicon and the passivation, I think I put them in green. I think we know how to handle it. So then the next question is, do we know how to make devices with it? And obviously, I think you're not going to do all the effort to go to 3,5 materials where you can have all this beautiful bandgap engineering stuff just to make a standard inversion mode device. Actually, you want to use this bandgap engineering to make quantum well devices, because they give you the advantage of much better electrostatic control, much higher carrier mobility. So these are the kind of structures that we propose. You make a buffer layer, and you can do this for 3,5, but you can also do it for germanium, with silicon germanium. You have a channel material, indium gallium arsenide or strained germanium, and you make a source drain on top of it. No ion implantation needed, that's why we call it implant-free quantum well. You grow all these things with epi, you make your 2D GaAs here, you make the quantum well here for the electrons, here for the holes, and you can actually make very good, very simple devices with it. Device structure actually is very simple. The real critical part actually here is the spacer length here, but that is, I think, beyond the scope of this discussion. The advantage of this kind of device is actually that it works as a fully depleted device. So if you look to a highly scaled MOS device and you look to the current leakage, you see that you tend to have a very big current leakage between the source and the drain. Going to quantum well devices, actually underneath the quantum well, you can make actually an isolated layer, which means that your current is completely limited to the quantum well, and you can actually completely kill this leakage effect here. So that's why these devices, is actually an illustration of a silicon germanium device you made that way with strain boosters. It actually performs extremely well. This is the red curve here. This is typical I-off current. So this is the on current of the device. This is the off current, which is a typical benchmark. If you look to the red curve here, which is the implant-free quantum well germanium device that we make, it compares, I think, very well with the very best devices that Intel has been publishing last year at the VLSI symposium. So I think this is a very, very encouraging result. It also shows you that the subthreshold slope actually is maintained even for very short channel lengths, indicating that we have a very good electrostatic control of these devices. You can also make these devices obviously in 3,5 materials. They look very simple. You make again a simple stack structure. You make an isolation structure here. Then you make a channel on top of it. You can either make a barrier, or you can also work without a barrier. In this case, we see that having an indium phosphide barrier on top of indium gallium arsenide gives us a very high mobility and actually gives us very good devices, good ion-on-off ratio, steep subthreshold slope. By the way, we also use these kind of devices to study the passivation and the differences between having an indium phosphide layer or no indium phosphide layer compared with ammonia vapor treatment that actually removes all the oxides and makes a sulfur passivation. And to make a long story short, just look to the DIT levels here for the indium gallium arsenide versus the indium phosphide. You see that actually the DIT close to the conduction band edge of the indium phosphide actually is higher here than for the indium gallium arsenide. So it's actually in this case not a good idea to have the indium phosphide layer, but definitely having the vapor deposition treatment actually is a very good idea. So that brings me almost to the end of the presentation. I've been talking about germanium PMOS devices. I've been talking about indium gallium arsenide NMOS devices. The big question is, what comes beyond the germanium PMOS devices? Can we also make 3,5 PMOS devices? Again, look to the list of materials that we have available. We have gallium antimonate, for example, here, which is a very interesting material for PMOS devices, very high hole mobility. And in the same table, actually, with the same lattice dimensions, we also have indium arsenide, actually, as a material with a very high electrical mobility. So this gave us the idea to make a very interesting combination and actually use this 6.1 category of materials, as we call them, so materials with a lattice constant of 6.1 to make the next generation of devices. For example, this is how a 3,5 PFET quantum well device could look like. We start with in this case, indium phosphide that we have grown the buffer on, aluminum antimonide, gallium antimonide, again, aluminum antimonide buffer, and we make actually a contact layer in indium arsenide as a contact layer. So this shows the stack that we have been growing. This shows the quantum well structure, and we think this kind of structure has lots of promises to use for PMOS devices because it has been demonstrated, at least calculated theoretically, that you can get very high hole mobility with these kind of materials. And these materials actually are very easy to grow, both on indium phosphide. We also have been able to grow them on germanium with very low defect densities, and they seem to be relatively easy to passivate also with aluminum oxide. So this, I think, already gives us an outlook for the next generation kind of devices. So that brings me to the conclusion of this presentation. What is the roadmap that we see towards ultimate CMOS? Well, I think if you look over the last years, we have made a transition from strained silicon with SiON to high-K metal gates. Having the high-K metal gates, I think, was a big deal because we got rid of the silicon dioxide here. We have seen in 22 nanometer that people are working with FinFETs, so that is probably also what people are going to use, I think, for the next technology generation. And then I think we see the 3,5 materials coming up. Maybe in the first phase, it will be germanium combined with 3,5. In the second phase, it will be full 3,5 materials. And when we introduce these new materials, we also might be able to see some new devices, which unfortunately I didn't have time to talk about in this presentation due to time limitations. But you can also imagine things like tunnel FET devices with heterojunctions and things like that coming up here in the 11 to 7 nanometer node. And beyond that, who knows, maybe it's graphene or some other kind of tunnel FET. So that was my presentation for today. Thank you for your attention.